Now let's look at the mean value theorem for integrals. It's a very useful theorem. And if you, let's go and write it down. You're going to need to be able to reproduce this on, oh, I don't know, a test or a quiz. Exactly. It says if f is continuous, and here my function is continuous. Now I have some extra squares here, so let me get them out of the way. If f is continuous on a closed interval, a, b, then there exists a number c in this closed interval such that the integral from a to b of f of x dx is equal to f of c times b minus a. Now, I do want to do this proof. What if this is just a constant function? Well, then this is kind of a trivial case. If f of x is a constant, then this is valid for all c, because that's exactly what the integrand would give you. It would be c times the integral of a to b dx, which is just, I guess it's f of c. F of c times b minus a. So that's kind of the trivial case. But what if it's not a constant? What if you have the situation right here where it goes up and down? Now the extreme value theorem tells us you can choose f little m, all right, and f big M, such that f is bounded by your minimum and your maximum values. So this right here is fm, little m, and this point right here is f big M on my diagram, all right? And all fx are squished between those two. So you remember that if a function is, we can apply the inequality theorem here, and we can get the integral from a to b of f of little m dx. Therefore, it's got to be less than or equal to the integral from a to b of f of x dx. And of course, this is bounded on the other side by f of big M dx. Now, let's look at what these functions look like. This is, oh, it's so hard for me to get back to my pen when this is going. F little m is this square right here, all right? And f big M is shown by this square right here. So f little m, if I do the integral from a to b of f little m, that is this yellow area right here, while the integral of the maximum is this kind of greenish square. All right, so we wind up with, this is a constant, so this becomes f of little m times b minus a. It's a lower bound of the integral from a to b of f of x dx. And that's f of big M, b minus a. So the area under this curve has got to be greater than the area under the small curve, under the minimum, if it were a constant, and it's got to be less than if the maximum were a constant. So let me divide through here by b minus a, because a and b are not equal, so I'm not having to deal with dividing by a 0 here. So this function is bounded. Now, from this last inequality, we know we can apply the intermediate value theorem. And there is a c in the interval a to b, such that f of c is 1 over b minus a times the integral from a to b of f of x dx. Or, if I rewrite this, b minus a times f of c, that's going to equal the integral from a to b of f of x dx. And that is our mean value theorem. Now, let's look at the definition of the average value of a function. The average value of the function, if I were to take it is equal to 1 over b minus a, okay, it's my closed variable, times the integral from a to b of f of x dx. Now, I'm not going to do this proof here because I've got a couple of other things I would rather do, but it's a pretty straightforward derivation there. Now let's find the average values of some functions. Now look at this. You see how this one goes negative and then it comes back positive? That's okay. Don't let that worry you. We're going to find the average value of this function between 0 and 4. So the average value is given by 1 over b minus a times the integral from a to b of f of x dx. All right. So this is 1 over, let's see, 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x. So this is 1/3 times 3x cubed divided by 3 minus 2x squared divided by 2, evaluated at 1 and 4. Let me rewrite this. It's 1/3 times x cubed minus x squared, evaluated at 1 and 4. All right, so this is 1/3 times 4 cubed minus 4 squared minus the lower limit. So it's 1 cubed minus 1 squared. That goes away, that's convenient. And I wind up with 1/3 times, let's see, 64 minus 16 minus 0. So this is 48, so that's 48/3. Now, the average value of a function can be very useful in physics. It turns out this is some data taken from the speed sound travels at different altitudes. And suppose we were to ask what the average speed of sound is. Well, we could actually find that on these intervals. And so the first thing you have to do is actually do this integration. All right, and we're going to find the average value is equal to 1 over b minus a, all right, times the integral from a to b of f of x dx. Now, f of x, in this case it's s of t, is, I guess I should be an x there, is this whole great big thing. So let me find b minus a. I'm just going to do this up front. This starts at 0 and goes to 80, so it's 80 minus 0. So it's 80. So this is going to be the multiplier, and I need to find I need to integrate all of those and add them together. All right, so let's do the first one. S1 is the integral from 0 to 11.5 of negative 4x plus 341. Okay, so it's negative 4x squared divided by 2 plus 341, evaluated as 0 and 11.5. Now I'm going to run out of room here, so I'm just going to give you the number. You can do this algebra. This is 3,657. S2 is the integral from 11.5 to 22 of 295 dx. So it's just 295 x evaluated 11.5 to 22. This gives me 3,097.5. S3 is the integral from, I guess it should be, velocities. Is the integral from, let's see, the third one is 22 to 32 of 3/4 x plus 278.5 dx. So that's 3x squared divided by 8 plus 278.5 evaluated at 22 and 32. And that gives me 2987.5. And then the integral from 32 to 50 of 3 halves x plus 254.5 dx is 3x squared divided by 4 plus 254.5x evaluated at 32 and 50. Okay, some of these get tedious. 5,688. And the final integral. Now none of these are hard, they're just kind of iterative. Integral from 50, 50 to 80. Got my things backwards. Of negative 3 halves x plus 404.5 dx. So this is negative 3x squared divided by 4 plus 404.5, and this is all evaluated at 50 and 80. And this gives me 9,210. So the integral from 0 to 80 of s of x dx is, I'm just going to add all these up, and I get 24640. Now, so my average value is equal to, so my average speed here, let's see if we can find it, is 1 over 80 times the integral from 0 to 80 of s of x dx. So it's 1 over 80 times 24640. So we wind up with 308 meters per second. All right, your turn. When you're done, turn off the video, finish your homework.